Right, so the next thing that we're going to talk about, which is actually going to directly relate to our last example, are our mutually exclusive events. Right, events are called mutually exclusive when they have no outcomes in common. In other words, it's impossible for both events to happen or occur simultaneously. Right, this is going to affect the way that we find answers to our OR probabilities. Right? Again, the idea, if we're thinking about mutually exclusive events, it's similar to the idea of disjoint sets back from chapter 2. There's no overlap between the two sets. There's nothing in common. So if we look back at these last examples, these sets are not disjoint because they had something in common. These sets are disjoint because they have nothing in common. So in this case, when our intersection is empty, that's an example of mutually exclusive events. This case is not mutually exclusive. Right? If A and B are mutually exclusive events, then what we can do in our formula is we can eliminate the subtraction that's at the end. Because since there is nothing in the overlap, we're basically subtracting 0, so there's nothing actually to subtract from what we have. Right? Again, just be cautious as you're going through things. We can only leave off the subtraction for mutually exclusive events. All right, so we're going to use our deck of cards again. Right? So again, as we're looking at these, remember that our row of spades and clubs are black. This other 2 rows here with our hearts and our diamonds are red. And we're going to use this to answer our next example here. All right, determine whether the following pairs of events are mutually exclusive and find our probability of A or B. Okay, so the first thing that we are asked to find the probability of A or B. And we need to first decide, are these events mutually exclusive? Right? So an ace and a jack. And what we want to do is we want to look at our picture and say, well, is it possible to be both an ace and a jack at the same time? Well, if we look at this, we have all of our aces down here, all of our jacks right here. So it's impossible to be both. So since it's impossible to be both in this case, we are going to say mutually exclusive. Right, so if we have mutually exclusive events, we can use for our probability of A or B our shortened formula, the probability of A plus the probability of B. So since we are mutually exclusive, we're going to use, again, our shortened formula. So our probability of either an ace or a jack, our probability of selecting an ace is 4 out of 52 because we have 4 aces. Our probability of selecting a jack is also 4 out of 52 because we have 4 jacks. That's going to give us 8 out of 52, which then we can reduce to 2 over 13. Right? So we were mutually exclusive because it was impossible to be both, so we just used our shortened formula. Right, for B, we're asked to find our probability of drawing an ace or a heart. So we have aces here. We have a row of hearts here. So it is possible to be both. We do have an ace of hearts. So this case is not mutually exclusive. Right? It is possible to be both. All right, so in that case, when we use our formula, our probability of A or B is going to be our probability of A plus our probability of B minus our probability of A and B. Right, so not mutually exclusive, we need to make sure we keep that subtraction in there. All right, so if we go for ace or heart, aces we have 4 out of 52. Hearts we have 13 out of 52. Both, there's exactly one ace of hearts. 4 plus 13 gives us 17, minus 1 gives us 16. So we get 16 over 52, which then if we reduce this into lowest terms, we get 4 over 13. So whether we're mutually exclusive or not is going to make a difference to whether or not we include that subtraction. All right, so let's do a couple more. Probability of a red card or a black card. This is going to be another example of events that are mutually exclusive. Right? It is impossible to be both. All right, so when our events are mutually exclusive, again, we can use our shortened formula. All right. So our probability of red or black. Well, our probability of drawing a red card, if we go back and kind of look at this, again, we're either in a red row or a black row, or not both. Red, we have 2 rows of 13, which gives us 26. Same thing is going to be true for the black. So we're going to have 26 out of 52 plus 26 out of 52. That is going to give us 52 out of 52, which gives us a probability of 1. Remember, a probability of 1 means something is absolutely certain to happen. So are we going to draw a red or black card? Yes, we're going to draw one or the other, right? We don't have any other options. We don't have purple playing cards usually, right? If we're using a traditional deck of playing cards, then our cards are either a red or black, so we have no choice but to draw either one. All right, and then our last one, a picture card or a red card. This one is going to be not mutually exclusive. Right? It is possible to be both. Right, so again, we're going to use our formula with our subtraction. Probability of A plus our probability of B minus our probability of A and B. All right, so probability of a picture, or sometimes we call it face card, or red. All right, so if we go back to our deck of cards, we have 3 different face cards or picture cards in our 4 different suits. So if we look at this, we have a total of 12. So 12 over 52. Plus the number of red cards, right? That was half. That was 26 out of 52. Right, now we're going to minus our probability of both. So if we look at this, we have for red face cards or red picture cards, 1, 2, 3, 4, 5, 6. So we're going to subtract 6 here. All right. If we do 12 plus 26, we get 38, minus 6 gives us 32. There's 32 over 52. Again, if we reduce this by dividing by 4, we get a total of 8 out of 13. Right? So when we're looking at mutually exclusive events, we're looking for OR probabilities, right? We're thinking, is it possible for the events to happen at the same time? And then based on our answer to that, then we are going to use the correct formula. Right? So whether or not we're mutually exclusive is going to tell us how we're going to calculate our OR probability.